Aim of today's experiment is to perform open circuit characteristic on a separately excited DC generator. The open circuit characteristic is abbreviated as OCC and is also called as magnetization characteristic, no load characteristic, or saturation characteristic. Now this characteristic is the characteristic between the generated voltage and field current for constant value of speed. So OCC is the characteristic between generated voltage and field current. Now we know that generated voltage of a generator is given by P phi and Z by 60A. In the equation number 1, P, Z, A, they are all constants. P is number of poles, Z is number of armature conductor, A is parallel path. So we can say that the generated voltage is proportional to phi into N. Now if we keep N also constant, if the speed is kept constant, then generated voltage will be proportional to field flux. Now flux generated in the machine will be proportional to field current, because we know that flux is given by MMF over reluctance, and MMF is equal to I into N, or we can say that the flux is proportional to current. In this case, it is the field current. Now this relationship will hold good as long as there is no saturation. So after saturation, this relationship will not hold good, and normally the characteristic will be linear and then the curve will bend as saturation creeps in. Now this is the characteristic which you will get for a machine which has not been previously magnetized, meaning thereby it had zero residual flux. Otherwise, for an actual machine, when we plot the characteristic will be something like this. It will start, even for zero field current, it will have some value of induced voltage which is due to residual flux. Why for we perform open circuit characteristic test? The open circuit characteristic test is required to obtain to predict the magnetization characteristic of the DC generator. After performing OCC characteristic, we will be able to predict the performance of generator under variable excitation. That is one. Second, we will be able to know the behavior of generator under the condition of saturation. We will also be able to find critical speed and critical resistance, which is very important when we are designing a generator. Now we will see what are the things which is required to perform this test. Now this, as I have already told you, that open circuit characteristic is the characteristic between generated voltage and field current. Now we will discuss what should be set up for performing this test. Now as we have discussed that this characteristic, OCC characteristic, is also known as no load characteristic, and it is plotted for a separately excited generator where you are keeping the speed constant and varying the field excitation of the generator. That means, what are the things which will be required? We will be requiring a generator. So first we will be requiring a DC generator, and this DC generator should be separately excited. Then we should have an arrangement by which we can change the field current from 0 to such a value where generated voltage is around 115% of the rated voltage. So that means you require an arrangement of variable field variable, and the field current should be variable from 0 to such a value of field current which will give us about 115% of the rated voltage. Now, when you are using a DC generator, that means you require a prime mover. DC generator can only work when we have a prime mover. So the third thing which we require is a prime mover. So for prime mover, we will be using a DC shunt motor. The reason for selecting DC shunt motor for prime mover is that speed can be controlled very conveniently. So the general setup should have a DC generator which should be separately excited. The field of the generator should be such that you are able to get field current variable. Of course, because it is a generator, so you require a prime mover. And what are the quantities which you will be measuring? See, it is the characteristic between generated voltage and field current. So you require a voltmeter to measure the generated current, and you require an ammeter to measure the field current. So let us now see what should be our circuit diagram for performing this test. So the first thing is you have a generator. So to operate generator, you require a prime mover. So I am starting from the prime mover side, which is a DC motor, and that DC shunt motor should have arrangement of speed control. We have already seen the speed control of DC shunt motor with the help of armature and field resistance control method. So the same circuit will be used here. So this is the input terminal. We are starting from the input terminal. Then it's a switch. We have seen that we use DPST switch, double pole single throw switch. Then you have fuse. We use HRC fuse. Then we will have a 3-point starter to reduce the starting current of the prime mover, that is DC motor. We require a starter. Now, in previous experiment of speed control, we used a 4-point starter. Here we will be using 3-point starter. Why? Because 4-point starters are used wherever you are controlling the speed of DC motor by changing field current in very large range. Because if you do it with 3-point starter, the hold on coil gets released. But in this particular experiment, we have to control speed in a very limited range. We have to run machine at a constant speed. There will be slight variation in speed when we perform experiment due to variation in input voltage or any other such reasons. And therefore, we will require speed control in very limited range. So even we can do it with the 3-point starter. The field resistance control method will not be used to that extent. So we are using a 3-point starter, which will of course be much cheaper than a 4-point starter. The first terminal of the 3-point starter is the line terminal, which is indicated as L. The second terminal is field terminal, capital F, and the third terminal is the armature terminal. So we then connect the armature terminal to a variable rheostat for controlling the speed of the DC motor by armature resistance control method. This is your armature of the DC motor, the terminal I am representing it as A1, A2. It can be any other notation also. Then A2 terminal goes back to supply through fuse and switch. So this completes your armature circuit. This is DPST switch, which will be operated by a single throw, and that is why you show mechanical connection between these two levers. The feed of the motor will be connected again through a rheostat so that we can control the speed by field resistance control method. This is F1 here, F2 here. So this completes the prime mover part. You have a DC motor with proper speed control arrangement so that you can perform your experiment at constant speed. Now this prime mover is mechanically coupled to armature of the DC generator. The prime mover is mechanically coupled to armature of DC generator. The terminals of armature of DC generator is represented as A1 dash and A2 dash. We are performing this test under no load condition. Therefore, we will not be connecting any load across the armature of DC generator. We have to measure the generated voltage. To measure the generated voltage, we will be connecting a voltmeter here. The voltmeter connected will be of moving coil type. Because we are using moving coil type of voltmeter, the polarity is very important. The field for this generator will be excited separately. So a separate arrangement for excitation of field will be provided, and the arrangement for excitation should be such that we are able to vary the field current from 0 to a value of field current which is required to generate 115% of rated voltage. So for that, we will be using our rheostat as potential divider. So I am drawing that arrangement here. This is the field, and the field should have variable DC input available, which is provided by using rheostat as potential divider. So this is your rheostat which is being used as potential divider. The supply to potential divider is of 220 volt DC supply, which will be fed to the potential divider through the DPST switch and of course HRC fuses which are connected for protection. We have to measure the field current also. Therefore, in the field circuit we will connect an ammeter. Ammeter will be of moving coil type. Again, when you are connecting moving coil type of instrument, you should be particular about the polarities. So this will be positive and negative polarity if the supply polarities are positive and negative here. So this completes our setup for performing OCC test on a separately excited generator. We will now be discussing that how to create a potential divider from a rheostat. We know from our background of rheostat that rheostat has three terminals, two lower terminals and one upper terminal. So if I draw this rheostat, now these are two lower terminals which if used will give you fixed resistance. So that fixed resistance will be fed to the supply. So here you are feeding the fixed voltage. Now with this arrangement, the voltage available at any turn of the rheostat will be V by N, presuming V is the input voltage and N is number of turns in the rheostat. Now this is variable point. Now from this variable point, we will be taking the supply, one end of the supply. The other end of the supply will be taken from here. Say if this is positive polarity and this is negative polarity. So if the variable point is at the starting position, then how many number of turns will be available at the output? It is 0. So voltage available will be 0. Now as you move this movable point, the slider of the rheostat towards the positive terminal, more and more number of turns will come into the output circuit, and depending upon the number of turns which are available at the output, we will get a variable DC voltage which will be able to vary the DC voltage from 0 at the starting position to V at the end position at this position. So that is how you can construct a potential divider. Now in this arrangement of potential divider, we have used a single rheostat. So the minimum voltage which we can get will be either 0, and the next step will be V by N. That means if we keep output number of turns 1, then this is the voltage which we will get. Now if we require a smoother control, then we can reduce the value of V by N. How we can reduce the value of V by N? The value of V by N can be reduced by increasing the N. So for increasing the N, instead of connecting one rheostat, we may use more than one rheostats. If we want a smoother control, then we can use more than one rheostats. By using more than one rheostat, we are increasing the number of turns, or we are reducing V by number of turns. So in this experiment, we will be using 3 rheostats. So let me explain you how you have to connect these 3 rheostats as a potential divider. Now first I am marking the lower terminals of all the 3 rheostats. So we will be feeding positive supply to the first rheostat here. Let me number these rheostats 1, 2 and 3. Then I connect these rheostats in this manner. The second terminal of rheostat 1 goes to first terminal of the rheostat 2 likewise, and the lower terminal of rheostat 3 goes to the negative side. So if we presume that each rheostat has n number of turns, so in this case voltage turn gets reduced to V by 3n. That means now I will get further smooth control. The output terminal will be taken from the variable point of the rheostat 3. So this will be arrangement which will be fed to the field, and then this goes back to the negative supply. So when the slider is at the initial position, output voltage will be less, will be 0. You move the slider when you completely exhaust all the turns of the rheostat 3, the voltage available at the output terminal will be V by 3N multiplied by N. So that means it will be V by 3, 1/3 of the input voltage. When you have exhausted all the turns, then the variable terminal will be taken out from this terminal. That means from the variable terminal of rheostat 3, we will now move our connection to variable terminal of rheostat 2. And then we will again start sliding it. When we exhaust this complete, we will get a voltage of 2 by 3 V. When we have exhausted all the turns of rheostat 2, we will move to variable terminal of rheostat 3, and likewise we will get a voltage which will be variable from 0 to V in the step of V by 3N. So that is how we can get a smoother control. Now we move to the experiment table where we will discuss further. We have seen the setup for performing this test. Now we will be discussing number 1, the procedure, that is how to perform this test. Number 2, the range of instruments to be connected. And number 3, the precautions which are to be observed. Now this circuit diagram is same as we have drawn previously when we were discussing the setup, drawn in a slight different manner. The terminals here are represented with notations AAA for armature terminals instead of A1 and A2, and for field the terminals are indicated as FFF instead of F1 and F2. The subscript used for motor is 1 and subscript 2 is used for generator. So the first step is we will connect the circuit like this. Then we will adjust the position of these two rheostats which are connected for controlling the speed of the prime mover. The field rheostat is set to 0 position. Otherwise, if it is kept to some higher value, it may result in very large speed of the prime mover. And the armature rheostat is kept to maximum position so that the starting current of the motor gets reduced. So we will feed the supply, DC supply, to the motor as well as to the field of the separately excited generator. We will not be connecting any load to the generator terminals. Once the supply is fed, the rheostats are adjusted to the position mentioned. We will bring the speed of the prime mover to the speed at which we have to plot OCC. In this case, we will be plotting OCC at the rated speed. So we will bring the generator to its rated speed with the help of these two rheostats. Once generator is running at rated speed, we will switch on the supply for the prime mover. Will not be feeding any supply to the field of separately excited generator. The prime mover will be brought to its rated speed with the help of these two rheostats. Once prime mover is running at rated speed, we will take down the reading of this voltmeter. Remember, we have not connected any supply to the field of generator. That means we have not given excitation to the generator. Under this condition, there will be slight voltage which will be appearing across the armature terminal of generator, and that is due to the residual flux. It will be in the range of 10 to 20 volts. Then we will feed supply to the potential divider so that excitation is available to the generator. We will gradually increase the supply to the field of the separately excited generator with the help of this variable slider of the potential divider. And for every adjusted value of the field current, we will take down the reading of the voltage generated across the armature. Throughout the experiment, we have to ensure that the speed of the prime mover is constant at rated speed. Now we will go on increasing the field current till we reach to 115% of the rated voltage. So this is how we will perform the experiment. Now next we discuss the range of the instruments which are to be connected. So what are the external instruments or equipments which we are connecting here? We are connecting rheostats, we are connecting a voltmeter across the generator terminal, and we are connecting an ammeter through which we can measure the field current. So we have to select the range of these equipments. So let us first talk about the voltmeter. Now the rating of the generator on which we will be performing this test, we have so far seen the procedure for performing this test. Now we will decide the range of the instruments to be connected for performing this test. To decide the range of the instruments to be connected, we have to see the nameplate specification of the machine. So this is the nameplate specification of the machine which will give us rating of the machine. So this is a generator which is of 3.7 kilowatt. The rated speed is 1500 rpm. The voltage is 220 volts. The current is 16.9 ampere. So these are the basic ratings of the machine. The rating of the excitation or the field is 220 volt, 0.9 ampere. So now we know that on which machine we are performing this test. So based on this, we will decide the range of first the voltmeter which is to be connected across the generator terminal. Now this machine has rated voltage of 220 volt. We have to excite this generator up to 1.15 times the 220 volt. That means we can use a 0 to 300 volt voltmeter. So voltmeter range will be 0 to 300 volt. The range of ammeter, the ammeter is to be connected in the field circuit, and the field circuit has rating of 0.9 ampere. That means an ammeter of the range 0 to 1/2 ampere will be sufficient for performing this test. So we have now decided the range of voltmeter and ammeter which is to be connected for this test. We have decided the rating of voltmeter and ammeter to be connected in this experiment. Now we will discuss the rating of rheostats to be connected. We are connecting rheostat for 3 locations here. One is for the field circuit. Now we know that the resistance of the field circuit is more than 100 ohms. So any rheostat which is of more than 100 ohm can be connected here. The excitation current is 0.9 ampere. So the current rating of the rheostat should be more than 1 ampere. So for this particular rheostat, we have available range of 125 ohms and 1.8 ampere. So that will be connected in series with the field of the motor. The armature we know has less resistance. Resistance is it is quite less. So here we can have a lower range rheostat. So the range which we will be using here will be of 20 ohms, 5.5 ampere. Now as we are performing this test under no load condition, so 5.5 ampere will be good enough. The second rheostat is connected as potential divider. As we have discussed during the setup process, that to have a finer control in the voltage here, output voltage here, so that we can control field current more accurately, we will be connecting three rheostats, and the rating of the rheostats will be 270 ohm, 1.4 ampere. So three such rheostats will be connected here in series to form a potential divider. Now once we have fixed the ratings to be connected, before we make connection and start performing experiment, we will discuss the precautions which are to be observed while performing the experiment. The precautions to be observed can be categorized two categories. Number one, generalized precautions, generic precautions, which is generalized and will be applicable to any experiment on electrical machine. Second, the specific precautions which are to be observed for that particular experiment. So first we discuss generic precautions. The generic precautions can again be divided into two categories: the precautions pertaining to the connection and precautions pertaining to the instruments. So first we discuss the precautions pertaining to connection. So the precaution number one is, whenever you are making any electrical connection, the connection should be tight. So every time you make any connection, ensure that connection is tight. Also ensure that there is no naked wire in the circuit. So wherever there is loose insulation, put an insulating tape at that location. So never use naked wires while making connection. The next precaution will be that before starting the experiment, you should get the connection verified from your instructor. Third, whenever you are performing experiment, you should perform it with wearing shoes, and you should stand on the insulating mat, as I am standing at present on the insulating mat. So these are the generic precautions pertaining to the connection. Then let us discuss the precautions pertaining to instruments. So whenever you are using instrument, you have to first ensure that there is no zero error. Now if you observe some zero error should be avoided, eliminated with the help of knob which is connected on the instrument. Then whenever you are taking reading, you should avoid parallax. So parallax error should be avoided. That is your second precaution. The third precaution is, the person who is observing the reading should loudly speak the reading, and the person who is noting down the reading should again repeat it, so that chances of error while writing can be eliminated. So these are the generic precautions which we have to follow for any experiments on electrical machine. The first precaution is that the test is to be performed at constant speed. You have to continuously observe the speed of the machine. If the machine changes, you have to bring machine back to its previous speed, for which you have connected these two rheostats. So machine should run at the speed at which you are performing or you are drawing the OCC characteristic. Second precaution is that while increasing the value of field current, at no time it should be reduced. That means if you are increasing the value of field current, it should continuously increase. It should never be brought back to some previous location, because if you do that due to hysteresis, you will not get the previous point. You will get a point, a voltage higher than the previous point. So this is another precaution, that you have to continuously increase the field current till you reach to the 1.15 times the rated voltage value. Now we have discussed the precautions. We will make the connection for the experiment. Now in this setup, we have option of using either digital instruments or analog instrument. We will be using the one which has better least count. So if I use a voltmeter, which I am required to read, the range of which we have decided as 0 to 300 volt, if I use an analog instrument of 0 to 300 volt, we will observe that its least count is 2 volts. The least, the analog voltmeter, which is available in the range of 0 to 300 volt, if we observe here, then we will see that its least count is 2 volts. See, between the two major division, it can measure 0 to 20 volt, and there are 10 number of smaller divisions. The least count of digital voltmeter which is available on this panel is 1 volt as compared to 2 volts of the analog instrument. So we will be using for measuring voltage digital voltmeter. Now we discuss the ammeter. The field current for the generator is 0.9 ampere. So we can use an ammeter of the range 0 to 1 ampere. Now we will decide whether to use analog instrument or the digital instrument. The analog instrument which is available in the range, for this range, is shown here. Now this particular analog instrument, if we select range of 0 to 1 ampere, we observe that for the range of 0 to 1 ampere, the main difference between the two main division is 0.1 ampere, and there are 10 number of smaller divisions. So least count here will be 0.01 ampere, whereas the least count of the digital ammeter available on the panel is 0.1 ampere. So on account of lower least count, we will be selecting analog ammeter of the range 0 to 1 ampere for performing this test. Now we will make the connection diagram for performing the test. We have decided the rating of the instruments to be connected. Now we will make the connection. This is the supply terminals. Here we have 220 volt DC supply available, which is made available here through a motorized rectifier. The supply will be fed to the line terminal of the 3-point starter. So we have a 3-point starter fixed over here. This is the location of 3-point starter. Its 3 terminals are terminated at this location. So first we connect line terminal to line terminal of the 3-point starter. Now whenever we are making a circuit, we will first draw the series circuit. Once series circuit is completed, we will connect parallel circuits. So if we see this diagram, we have reached to the L. Now from A, that is A terminal of the 3-point starter, we will be feeding power to armature of prime mover, that is motor, through the rheostat. So we have to connect a rheostat. We have selected a 20 ohms 5.5 ampere rheostat to be connected in series with the armature circuit. So this is the rheostat 20 ohm 5.5 ampere which we will be connecting. In the rheostat there are 3 terminals, 2 lower terminals and 1 upper terminal. When we are using rheostat as a variable resistance, we will be connecting one of the lower terminal and this upper terminal. So we make the connection from A terminal of the 3-point starter to one of the lower terminal of the rheostat. So here we connect one lower terminal. Now in precautions we have discussed that the field rheostat should be connected to the maximum position. So the slider will be brought here. See, power is being fed from the supply. So this is the direction of current. Current direction will be this. That means if I have connected circuit and brought slider here, then the complete resistance is into the circuit, and this will then be fed to the armature terminal of motor, which is A1 here. The second terminal of armature of the motor is AA1, which will be brought back to the negative terminal, brought back to the supply at its negative terminal. So AA1 terminal, second terminal of the armature of the motor, goes back to the negative terminal of the supply. So see, I have completed the series circuit from 3-point starter's A terminal to one terminal of the armature of the motor through the rheostat, and the second terminal of the armature of motor goes back to the supply. Now we connect the parallel branch. For connecting parallel branch, in parallel branch we have to connect rheostat of rating 125 ohms 1.8 ampere. So this is the rheostat which we will be connecting from field terminal of 3-point starter to one of the lower terminal of the rheostat. The other terminal, other connection is taken from the upper terminal, and that goes to first field terminal of the motor. The second field terminal of the motor has to go back to negative terminal of the supply. Another option is I may connect it directly to second terminal AA1 of the motor, which is already going to the negative terminal. So this connection will require a smaller length wire. So we will be connecting double F1 terminal, that is second terminal of the field of the motor, to second terminal of the armature of the motor. So this completes our connection of prime mover side. Let us recheck. Positive terminal of the supply goes to L terminal of the 3-point starter. The armature terminal of the 3-point starter goes to rheostat, which is kept at its maximum position. The variable terminal of the rheostat goes to first terminal of armature of the motor. The second terminal of the armature of the motor goes back to supply, negative terminal of the supply. The field circuit, the field point, F point of the 3-point starter goes to one lower terminal of the rheostat, which is to be connected in series with the field. The variable point to the first point of the field of the motor, and the second point of the field of the motor, double F1, goes to the second point of the armature terminal. The field rheostat is to be set to minimum resistance position. So let us observe whether we have connected it correctly or not. So from here, this is the direction of current which will flow, and see, I have connected it at the correct location. If I would have connected it to the other side, then the complete resistance would have been into the circuit. So I have to connect this rheostat to its least resistance position. So slider is kept here. Now we will connect a voltmeter across the armature terminals of the generator to measure the generated voltage. We have decided that we will be using digital voltmeter because of its lesser least count. So we will be using digital voltmeter V1. So the armature terminal will directly be connected to these two terminals of digital voltmeter V1. So A2 terminal goes to positive terminal, and double A2 terminal of the generator of the armature goes to negative terminal of the digital voltmeter. Now if we reverse the connection, then the voltmeter will indicate the reading but with negative sign. We have connected voltmeter across the armature terminal of generator. Now we will be connecting 3 rheostats as potential divider, and we are selecting 270 ohm 1.4 ampere rheostats. So these are 3 rheostats. Which we will be connecting first in series. So let me connect them in series first. I will be connecting all the lower terminals. See the first lower terminal. See, I am keeping this rheostat as my topmost rheostat. So this lower terminal of this rheostat will go to the positive terminal of the supply. The second lower terminal of the rheostat will go to one lower terminal of the second rheostat. The second lower terminal of the second rheostat will be connected to one lower terminal the third rheostat. And the second terminal of the last rheostat will be connected to the negative terminal of the supply. So what we have done here is we have connected three rheostats in series, and across these three series connected rheostats we have fed DC supply. Now one variable terminal will be taken from the third rheostat, will be fed to the field of the generator. The second terminal of the field of the generator, see, this is the connection. The variable terminal from the potential divider goes to first terminal of the field of the generator. The second terminal of the field of generator will be connected to an ammeter. We have decided that we will be connecting analog ammeter because of its lesser least count as compared to the digital ammeter which is available on the panel. So the second terminal of the field of the generator is connected to positive terminal of DC ammeter. The negative terminal of, or the range terminal of the DC ammeter will then be going back, or will be connected to the negative terminal of the supply. So this is the connection from the negative terminal of the ammeter to negative terminal of the supply. So this completes our circuit of the field of the generator. Let us recheck. So let us recheck the circuit of potential divider. We have connected three rheostats in series. So this is the first terminal of the topmost rheostat. Say I number it as rheostat 1. So the first terminal of rheostat 1 goes to positive terminal. The second terminal goes to one terminal of the second rheostat. The second lower terminal of the second rheostat goes to one lower terminal of the third rheostat. The remaining lower terminal of the third rheostat goes to the negative supply. The variable terminal of the third rheostat is connected to the field of the generator, and field of generator is connected to an ammeter to measure the field current, and that is connected back to the negative terminal. So this is a correct circuit. Now we observe the location of the variable slider, the position of the slider for the third rheostat. The slider position in the remaining two rheostat is redundant. Why? Because we are not connecting the variable terminal of those two rheostats, and that is why I can connect it anywhere I like, because I have not connected a variable slider, so I can connect it at any location I desire. Whereas slider for the third rheostat should be connected so that minimum voltage is available for the field of the generator. Now, if it is connected the way it is connected here, we will observe that this complete voltage will be available. So I have to bring it to this initial position. If I am connecting the slider to this position, there will be zero output turns available for the field circuit of the generator. That will give us zero current. So this is the connection. Now we will feed supply to the panel. Now we require first AC supply so that the digital instruments can work. The digital instrument of our interest in this setup will be voltmeter V1, which will give us voltage generated by the generator, and this speed indicator, which will be giving us the speed of the generator or speed of the prime mover, which will be same because they are both coupled. We have already connected the rheostat of armature and field circuit of the motor at the desired location, at the desired locations. Now we will feed the DC supply to the setup, and then we'll observe that it should be 220 volts supply. So we have started the DC supply, connecting a multimeter to observe the voltage, input voltage, so which is 219.5 volt, so which is almost 220 volts. Now we start the prime mover. The prime mover will be started with the help of 3-point starter. Now whenever you are moving the handle of the 3-point starter, you have to ensure that the handle is moved gradually. It has to be moved very gradually. So the speed is 1193 rpm, whereas we require 1500 rpm, which is rated the speed of the motor. The reason for this very low speed is that in the armature circuit we have connected the complete rheostat. So we will reduce the rheostat which is connected, reduce the resistance which is connected in series with the armature circuit. And as we cut out this resistance, we will observe that the speed of the prime mover will increase. So see, the speed is increasing as I am reducing the external resistance in the armature circuit. Now I have exhausted the complete external resistance. That means under this condition there is no resistance connected, no external resistance connected in series with the armature of the motor. Even then the speed is not the rated speed that we desire. It is 1457 rpm. That means we have to increase the speed. To increase the speed, we will reduce the flux generated by the field of the motor. That means we connect external resistance now into the field of the prime mover. So I am inserting external resistance and observe, as I am inserting the external resistance, speed is increasing. So I have to bring this at 1500 rpm. So this is the location. At this position, I have not yet given any supply to the field of the generator. The slider is at 0 position. That means this rheostat, this variable terminal is at 0 position. So no supply is available to the field. Field current is 0 as indicated by this ammeter. Even then, the armature is indicating a voltage of 20 volt. This is due to residual flux. So we start taking the observation. The first observation is field current 0 and the generated voltage is 20 volt. Kindly repeat whatever I do.
Field current is 0 ampere and voltage is 20 volt.
Just observe here that the speed has slightly increased. So I will bring it back to 1500 position. This change in speed may be due to slight variation in the input voltage, which might have changed slightly. So throughout the test, we have to keep the speed constant at 1500 rpm. Now this test we could have performed at any desired speed. So we are at present performing the test at 1500 rpm. Now I will be feeding supply to the field of the generator and the generated voltage will increase. Field current is 0.015 ampere and the generated voltage is 25 volts.
Field current is 0.015 ampere and the voltage is 25 volt.
Field current is 0.03 ampere. The generated voltage is 31 volts.
Field current is 0.03 ampere and the voltage is 31 volt.
Field current is 0.05 ampere and the generated voltage is 40 volts.
Field current is 0.05 amperes and voltage is 40 volts.
So this way we will be sliding this slider towards the lower terminal of the second lower terminal of the third rheostat. Thereby we will be increasing the voltage fed to the field, and for increasing field current we will note down the reading of corresponding voltage, which, to reduce the length of the video, we are not showing all the readings, which will be made available to you at the end of the video in the description box. Now we will say exhausted the first rheostat, the lowermost rheostat. At this location, the field current is 0.2 ampere and the voltage is 100 volt.
Field current is 0.2 ampere and the voltage is 100 volt.
As we have exhausted the lowermost rheostat, now we will change the position of the variable point to the second rheostat. And if I am now using the second rheostat slider or the variable point should be brought to such a position where initially 0 number of turns are into the output circuit. So that means it will be brought back to this position. Now we will switch off the supply and change the position of variable point from rheostat 3 to rheostat 2 with rheostat 2 slider in such a position that initially no turns are available of the second rheostat. Only number of turns of the first rheostat, third rheostat will be into the circuit. As we have exhausted the third rheostat completely, we will now change the location of the variable point. The variable point will now be brought to the variable terminal of the second rheostat with the slider to this particular position, so that at the output circuit we have only n number of turns available, where n is number of turns in one particular rheostat. Now from this location we will restart the circuit. Now we increase the input voltage by sliding the slider of rheostat 2 to the other side. The field current is 0.22 ampere and the generated voltage is 110 volts.
Field current is 0.22 ampere and voltage is 110 volt.
Likewise, we will continuously increase the field current, and for each adjusted field current, we will take down the reading of voltmeter and we will exhaust the second. Now we will increase the field current, and for every adjusted field current, we will note down the reading of voltage generated. 0.02 ampere, 28 volts.
Field current is 0.02 ampere and voltage is
field current is 0.04 ampere and the voltage is 35 volts.
field current is 0.04 and voltage is 35 volt.
Likewise, we will increase the field current continuously, and for every adjusted field current, we will note down the reading of voltage appearing across the generator terminals. So we have almost exhausted the third rheostat.
0.18.
0.18 and the voltage is 101 volt, is 100 volt.
Field current is 0.18 and voltage is 100 volt.
So we have now exhausted the third rheostat. We will now switch the position of the variable point from the third rheostat to the second rheostat. For that, we will switch off the supply first to stop the motor, and then we change the position of the variable point, bring it to the variable point of the second rheostat. Now position of the slider of the second rheostat will be important. Earlier it was not important because we were not using variable terminal. Now we are using variable terminal. So this should brought back to such a position where external windings which is connected to the field circuit of this second rheostat should be 0. We will restart the motor. And then we will start increasing the input voltage. And for every adjusted field current, we will take down the reading of generated voltage. So we have now fully exhausted the rheostat 2. The reading is 0.38 ampere and the voltage is 167 volt.
Field current is 0.38 ampere and the voltage is 167 volt.
Now we will switch the variable position from rheostat 2 to rheostat 1. For that, we will switch off the supply and then we'll restart the motor again. And now we have moved the variable position from rheostat 2 to rheostat 1, and we have brought the slider of the rheostat 1 to its initial position. Now we will increase the position of rheostat, and for increasing field current, we will note down the reading of generated voltage. So we have exhausted the first rheostat also. The reading of field current is now 0.88 ampere and the voltage is 233 volt. So this completes portion of our reading part. Then we will be plotting. After this, we will be plotting the characteristic between generated voltage and field current.